This is a presentation of Chapter 4, Section 4 in the 8th grade notes, Scientific Notation. We'll go ahead and start off with the definition of scientific notation. Scientific notation is a method of writing very large or very small numbers by using powers of 10. Obviously, you can guess from the name that this is primarily used in the sciences when we're looking at, as they said, very, very, very large things or very, very small things. Generally things that are microscopic or things that are so large we could not express them in a simple way of writing. Usually those refer to things that are distances in space, the distances, different constellations, and things like that. Scientific notation carries on from where we've been because this is really all about powers and exponents. So if we have that base knowledge of powers and exponents that we gained in 4.1 through 4.3, then we should be okay when it comes to writing things with scientific notation. So let's start with number 1. Now number 1 is actually already written in scientific notation, and what they're going to have us do in number 1 here is actually take and go the other way to write this in standard notation, or to write this as a regular number. So in question A there, they've got 1.35 times 10 to the 5th. And again, this is written in proper scientific notation. Let's talk about the different components of scientific notation here. Scientific notation is always a multiplication problem, and the first part is always going to start off as something that's written between 1 and 10. So clearly 1.35 qualifies, that is between 1 and 10. Then it's always times 10 to the something. It's the number 10 because our numbering system revolves around the number 10. As we saw when we talked about very specifically with the negative exponents, but it would apply to the positive exponents as well, though that 10 is how we generate our place values, like tenths and hundredths and thousands, and on the left side of the decimal, tens and hundreds and thousands and 10,000s and 100,000s and millions and so on and so forth. And then the exponent is going to represent how many times we would kick a decimal out. That's what's going to make that number be very large and something we would not generally write, for instance, in a scholarly journal. Now, obviously, the numbers you're working with here in the book are not nearly as big as what we would normally use scientific notation for. However, it's the same meaning whether that exponent is a 5 or 105 in terms of what we're writing. What we're doing is still the same. So a lot of you would be prone in looking at this question to go ahead and get the calculator out and multiply. But it's really not that difficult. Again, the exponent is related to the place value. The exponent tells me how many times I'm going to kick the decimal out to generate the number I need. So I really don't need a calculator to do this at all. Since the exponent in A is a 5, all that simply means is the decimal's been moved 5 times. So to change it back to a number, I just need to move it back out 5 times. So here where I have 1.35, I'm going to throw the decimal 5 times to the right. Why? Because the exponent is 5. And when I do that, as you can see, we have a bunch of jumps there. Some of them cover numbers that are already there, some do not. Those ones that do not get filled in with zeros, and that's how we end up with 135,000. Let's go down and look at C there. We've got negative 2.01 times 10 to the 4th. Now, don't let the fact that this is negative bother you. The fact that this is negative is really just there to mess with you. What's important here is that the exponent is 4. Since the exponent is 4, that means the decimal's been moved 4 times. So I need to throw the decimal 4 times out. And when I throw that decimal 4 times out there, 2 empty jumps, as you can see at the end, filling with zeros, and we end up with negative 20,100. Now you can see I intentionally skipped question B there. Let's go back and talk about B and what makes B different. B has a negative as well, but what makes B different is that the negative in this particular question is on the exponent. When the exponent is negative, as you recall, when we had those questions in an earlier section like 10 to the negative second and 10 to the negative first, we saw that those were decimal place values like the hundredths and the 10,000ths place. All right, so we know that that's going to generate somehow a decimal. So what's different when we have a negative exponent, in order to generate that decimal value, we're not kicking the decimal to the right to solve this. We're actually going to kick the decimal to the left. As you can see, what they've done there is they've actually solved out 10 to the negative third as 1 over 1,000, and then shown you that they're doing 2.7 over 1,000, which is how we get this. But again, it's much simpler than that. We're moving the decimal 3 times out, but again, because it's a negative, and again, those negatives generate decimals, we're going to throw the decimal to the left here. Empty jumps are still going to fill in with zeros, and as you can see, 0027 is exactly what we have down here for the solution. So now what they're going to do in question number 2 is they're going to go ahead and let us go the other way. They're going to start with the number and have us write something in scientific notation. So they've got 0.00709. So since this is one of those decimals, we know that the exponent has to be negative in our scientific notation question. So that's one mystery solved. We know that that exponent, when I write it onto that 10, which is again part of our numbering system, that's how I'm going to get that decimal value. To start, as I said in the introduction, it's got to be something between 1 and 10. So you're going to drop the decimal into that number somewhere else so it changes into something that is between 1 and 10. Well, if I put the decimal after the 7 and before that 0 that's right after it, that's going to make it say 7.09. And that is indeed how we change that into something between 1 and 10. Again, it's always times 10 for the next part. That's not a question because, again, for I think the third or fourth time in this presentation, I'm saying to you that our numbering system revolves around the number 10. So that's where the 10 comes from. The exponent is how many times we move that decimal. And that's the one thing you don't see here yet because that's what they're explaining here. To get the decimal to that place where it's after that 7, we would have had to move the decimal 3 times. And again, since it was a decimal, that's how we know that it had to be negative. So that's why the exponent ends up being -3, which is what you can see here in the gray box. 7.09 times 10 to the -3rd. That is in proper scientific notation. What they do there then is they check it with a calculator actually multiplying, and they end up with 0.00709, which is what you see they've generated there with the calculator, the same as our original multiplication question. All right, let's go ahead and take a look at the next question here. The next question says, a pencil is 18.7 centimeters long. If you were to lay 10,000 pencils end to end, how many millimeters long would they be? Write the answer in scientific notation.